So today I'm gonna first start to look at a couple of examples for the moment of the couples, and then if you have time, we move on. Let's see where we can do. So the first example is a 2D. Object looking like this. So we want to calculate the moment on that plane, so the moment you have applied on that object. That's all. The supports there, one there, some support to hold it in place there. So if you look at it, I can go ahead and say, hey, this problem, I can break it into the three couples before doing anything. So I can go and say, I have the 200s, 300s, and 450. So we'll start with the 200s. So if I go ahead and say, I have 200, and then I have 200s here. And if I continue that line of action, this is going to be 4. So that's the first one. I'm going to just calculate the moment for that. So the moment of the cut was ft. Again, assuming, because the 2D, you have to assume the positive direction. So assuming the counterclockwise is positive. So the moment here is one of the forces. It's going to be one of the forces, which is 200, times the distance between them, which is going to be 4. Is it positive or negative?
Negative 800. It's going to rotate clockwise.
Okay, so if you rotate clockwise, it's going to be negative 800. So, negative.
So are we to assume that it's going to, what point are we assuming it's rotating around for this 200?
Do you remember the last time it says the couple is free moment?
Oh, it doesn't matter. Yep.
doesn't matter, you can put it anywhere that you want.
Yep.
Then we will go to 450. So I have two more forces and it's 450. So 400, 450 this way. Then I have 450 this way. So, and the distance between there is 3. And so the moment would be one of the force times the distance, so 450.
Positive 1,350.
So rotate counterclockwise, so it's going to be positive. How much is that?
1,350.
Positive. And the third one would be the 300. So I have the 300 going like that. 300. 300. And the distance between them 5. So I'll just became 1 and 2 and 3. So it's going to be 300 times 5 and positive or negative.
Negative. So negative 1,500 or 1,500.
Counterclockwise, negative. So negative 1,500. Just 1 meter. So then the m will be just adding the ft, or it would be m1 plus m2 plus m3 is negative 800 plus 1350 minus 800. So if I have it all correct, it should come out to 950. Negative 900. Negative 950 Newton meter. So let's also look at the 3D problem. So if you have the x, y, z, let's say x, y, z, and then we have object is going in the x direction. There. two forces applying on that. So one of them play on here, on here, the other one play on here. So, if we have this one and we want to find the moment of the couple again, 3D, same thing, so it's going to be N, it's going to be R, N. So, in this case, if I want to calculate the moment, I have to find the R, I have to find the F. So the book did it in actually 3 methods. So the first method I'm going to work on that is the second one, the middle. Assuming it's a couple, so I have a couple. The couple, if I have a couple, the moment from them is going to be one of the force times the R that connect two forces. Remember? So if I have a couple like that in 3D, there was an R going from one of them to another one. M would be R cross F. So in this case, if I want to consider the R is going to be going between them, it's going from here to here. So that's going to be the R. So it's going to be R, A, B. So the moment that I'm on my right here is going to be M would be R, A, B times the F at point B. Cross the F at point B. So I have to find these two. First of all, I have to find the RAB. So the RAB is second minus the first one. YB minus YA, K plus ZB minus ZA, K. So here, so I know O is 0, 0, 0. The point A is on the x-axis. It doesn't have an x, it's on the y-axis, so it doesn't have an x or z. So the point A would be 0, 8, and 0. And the point B, how much is the coordinates for the point B? I know that So I need to find, if I go ahead and for example say, assume I call this point C, I need to find, in that triangle, I need to find these lengths and these lengths. So if I draw that triangle here, this is the A, this is the B, and this is the C, and I know that this is 6, this is 6, and this is 30. So how much would be this one? 6 cosine 30.
5.2.
6 cosine 30 is 5.2. And this one is 6 sine 30.
It's 3.
3. So here, if I want to show it, so this distance would be so distance would be 6 cosine 30, which is 5.2. This one is 6 sine 30, which is 3. So the coordinate for that, for the point C, the x is going to be 5.2. The x, the y would be 8, and the z would be negative 3. Right? You want to follow, just to make it just look like the book, because the book didn't do it like that, I can rewrite it like that, so it's going to be the x is 6 cosine 30, 8, and the y is minus 6 sine 30. This is how the book writes it, in case that you want to follow it right, like it. Anyway, so if I go ahead and put it there, it's the R, A, B. So B minus R, I'm gonna just follow this, so it's a 6 cosine 30 minus 0I plus 8 minus 8 J plus minus 6 sine 30 minus 0 J. So that's it. That is that's the R. What about the F? How much is the F? F at point B. So F at point B is parallel to the z-axis.
So would that be 0?
So if the vector is parallel to the axis, remember that always any vector, so assume vector R is its magnitude times the unit vector, like that. So this one is going to be its magnitude times the unit vector along the B, and unit vector along the FB, along the FB the unit vector along the FB is the same as the unit vector on the z-axis, right? The unit vector FB is on the z-axis, so its unit vector is the same as the unit vector on the z-axis. And the unit vector on the z-axis is k. So it's going to be its magnitude, which is going to be 25. Because in the z direction, k doesn't have the I or j component. Then m r cross f, which would be, you can use that determinant I j k for the r 6 cosine 30, 0 minus 6 sine 30, and for the k, we have the 0, 0, 5. I can solve that, so it should, if everything is put in the correct format, it should come out as minus 130 k. By the way, the distances are in inches, not feet. So it comes out as 130 on the inch. One other, the first method that the book, so this is the second method in the book. The first method that the book did is that instead of going that way, it's going like this. M is sigma RF. So it's going to say that it calculates the moment for each force separately, and then they add them together. So it's going to say it's going to be R times F at A plus R times F at B. And for the A, it says, okay, for the A, the R would be OA. For the B, the R would be OB. Basically says, you can calculate, you can find the R OA times for the F, is going to, because it's going downward, minus 25J plus ROB, whatever it is, you can find it, and the F, which is plus 25J. And if you find the ROA and ROB and do the calculation, eventually you get that 130J. So this is another way of doing that. Calculate the moment for each of the forces. So quickly, these are the three axes. And I'm not going to draw the integral, I'll just draw the forces. And there are one force is here, and another force is going down here. I said, okay, that's fine. That's it. R O A. That's the R O B. These are the point O, point and then add them together. Um, so what it did here just went and calculated the moment for each of the forces separately, add them together in this the first method the book did. The second method I use it because the topic of the topic we're covering is that no, they are coupled or equal in the opposite direction, so just use the coupled formula to do the calculation. Question?
So that one's more useful if the forces aren't equal.
If the forces are not equal, you cannot do it this way because they're not coupled. That's the only way that you can do it. But if they are equal and opposite, then you can either do it that way or this way. Generally, I suggest you to do it this way because this is the one that I think is less confusing. It's more work, but less confusing. Okay. Next part, we're going to talk about if you have a system of forces and the moments, how we can simplify them. And this is one of the things, actually, when we get to the strengths of material, we are going to use them. So let's look at, there's a couple of rules that we're going to look at them and eventually work ahead of them. Assume I have say beam like this, and there is a force applying at the end of that. Okay. Can I say equal? force is there. If I want to add a force here at this point, same as that one. Are these two equal? How can I make them equal? What if I go ahead and add another one here? What now? Are they equal? See, the green one would cancel the red one. Although I have them there, it will cancel the red one. So now, can I go ahead and say, let's do it one further step. Can I say that one is equal to this one? Can I say that? So what, if they are equal, what's the difference between the first one and the third one? Or what does it show, the first one and the third one? We use that principles a lot previously. So it tells you that you can move a force along its line of action. You can slide the force along its line of action and nothing will change. So if in this case it shows that if I have a line of action, I can be, so like I said, force can be slide line is line of action. So if I consider that force and the line of action of that force, I can move that force back and forth. I can slide it back and forth to any position along its line of action. And it's exactly, again, still it's going to be the same system. Question? So we use that a lot when we wanted to calculate the moment, but usually see we slide the force back and forth to see where's the easiest way to calculate the distance or to understand which direction it's gonna rotate. Now let's look at, so this is this way. Now let's look at another one. If I go ahead and again I have a beam. This time, instead of having it up, so having it in the direction of that, I'm gonna say, you know what, this time I'm gonna put the force there. And we call this point O, and call this distance D1. So now I go ahead and say, you know, I will draw that. I would have the F there. But this time, I would want to have two forces. Okay, at that point. They're here. And they're here. Are they the same? Are the same? Okay. Cool. Now, if I go ahead one more step, says same as before. And assume this distance is D2 and D3. Go ahead and have them there. And only put the F. So, is this last one same as the first one? They are not, why they are not?
The distance is lower.
Still sigma of y is 0. Still sigma of y is the F.
So just looking at the force.
No, everything. If they are not equal, why they are not equal? Because the amount of force in the y direction is the same. So, here, how much the moment here? At what point? How much moment it force F about point O.
F times D1.
So in the case one, it's going to be F times D1. And it's not rotating like that. No, it's rotating like that. Right? What about here? What's the moment about point O? The second case.
F times D2 times D3. D2 plus D.
The same thing as D1. Because these two will cancel each other eventually. The moment of these two, whatever is that, this one is the opposite of that. So the moment of this would be opposite of that. So that two would cancel each other. It still is going to be F D2 plus D3 or F D1. Agreed? How much is the moment here? FD2. So this way, all of them this direction. So when I'm moving the F from the tip to somewhere in here, M3 is equal, less, or larger than the M1.
Plus.
The M3 here, the moment here, is smaller or larger than M1.
Are we talking about like directions
No, just the magnet.
and less?
It's gonna be less. Because the distance is smaller here, D1, here is just D2, very small. So, by moving the force from here to here, what happened? I'm losing the moment. I'm losing the moment. Agreed? So I'm losing the moment. How am I going to compensate for that moment? How much I lost the moment? So that's the difference between these two. So the difference, the delta M, is how much I lost the moment. Is the difference is the M1 minus M3, which would be F D1 minus F D2. Agreed? So how much is that? F D1 minus D2, which would be D1 minus D2 with D3. That would be F equal D3. This is how much moment I lost. Right? This is how much moment I lost. So I have to compensate for that. So how am I going to compensate for that? So I go there. When I bring the force from here to here, I'm gonna add that much moment there. So I'm gonna say, you know what? I'm gonna say add M equal to F D3 to that point to compensate for the moment I lost. So when I move the force, if I'm moving it along its line of action, if I move it along the line of action, that's okay. But if I move it but it's not along the line of action, I have to compensate for the moment that either I generated or I lost. It's not that always I'm losing, assume it was the opposite. I would assume F was here and I move it to the tip, like here. I just assume the first case was like this. I have the force here, and then I want to move the force to the tip. So if I move it to the tip, what's the result of moving it to the tip? If I bring it from this time, assume I bring it from here, bring it here. If I want to say 1, this is 2. So I want to go from here to there. If I move it from here to here, what happens? I actually increase the moment. So now I have to compensate for the moment I increased. So I have to go and add the negative of the moment I increased to compensate for that. So in this case, I have to put the moment opposite of whatever I decrease to compensate for. So if this is, for example, the distance between these two are d4, I have to add the m equals f d4 to compensate, this time to compensate for the moment I actually compensate for the moment I generated, I increased. So the entire idea is like that. If you are moving the force around, you have to make sure that you compensate for the amount of moment you either decrease or increase by moving it around. So you got the idea? If it goes along this line of action, you don't need to do anything. But if you move it other than this line of action, you have to compensate for it. And it's not only in 2D, you can do it also in 3D. In case that, for example, we need to move the assume we have the 3D object, and there are 3 forces on it. It's just a single case. In general case, assume we have an object that there are, for example, 3 forces on it. You can bring all the forces together at single point. This is eventually what we want to do. So eventually what we want to do. If, for example, I have an object that has 4 or 5 forces applying on that, I want to make sure and say that, okay, I'm going to bring them all to one point. I will bring them all to single point, and then I will add the moment to compensate for the amount of the moment. Either I lost it or increase it or whatever. So basically, this is what we want to do. If you have system of forces and moment, you might have some moment as well. We want to bring them all to the single point and add them together. And this is how we are going to do it. We move it force by force, and then we compensate for the moment that we have.